In this video, we'll learn all about lambdas. So starting with the code from last video where we define these various different sums, cleaned up a little bit, I've tucked each into functions so we can run them when we want to. But for each one of these different sums, we had to define helper functions, right? If we wanted to sum all the integers between a and b, we needed an identity function and an increment, and then we passed those into sum here. If we wanted to sum all the cubes of integers, we had to first define a cube function and an increment, and then we passed those into sum. Same thing with pi sum, we define pi term, pi next, and passed those off into sum as well. But for each one of these helper functions, we give it a name, we pass it to sum, but then sum immediately renames that procedure. The thing that does the multiplying three things together, the cubing, the procedure object that represents that process, is first name cube, and that name persists 2 lines until we pass it into sum. Sum passes the value of cube, the procedure object, into this function and gives it the name term, and then does all the work as this new variable called term bound to the procedure of cubing. So wouldn't it be nice if we didn't have to bother creating a brand new procedure every single time we wanted to have these one-off functions, right? If I wanted to pass an integer into a function, I wouldn't say define x to be 3 and then pass x in. I would just say pass 3 into whatever function. That's the idea behind lambdas. It's that for functions. So if we only want a function for a single use, why bother naming it at all? Why not just have the procedure object itself, the thing representing the process, and give that to whatever consuming higher order procedure will use it? So the syntax for creating a lambda, or this anonymous function, is as follows. So it's a combination here, starting with the keyword lambda. We have then a list of parameters, very much like a function body, very much like a function signature, and then we have the list of different expressions that make up the body of the lambda. Now the value of the entire lambda is just a procedure object. So this is a special form. So it's a special form because you can't just evaluate it in terms of applicative order. So we can't just say this is some function called lambda and then combine these using regular eval and apply. So take the first parameter and use it as the function for the remaining parameters. That doesn't make sense. And similarly, the different bodies wouldn't line up properly with things that necessarily have values. So if we treated that as a regular form, it wouldn't work. So this is a special form. That special form says create a procedure where this is the sequence of expressions to evaluate once we apply that procedure to something. And this is the list of symbols to use as parameters to be bound to the argument values, again, once we apply it to those values. So what a lambda does is it creates an unnamed procedure, so it creates a procedure object without binding it to a name, unlike the define function that we had. It's a lot like creating literals for functions. So instead of saying x when we need to say 3, we can just say 3. Same thing for functions, we can just say lambda, and then here's the process for a function. Okay, so the name lambda comes out of lambda calculus, which you might recall is sort of the origin of functional programming. But you can just think of lambda as meaning make procedure. It's just a fancy word that says make a procedure that takes in these parameters and does this sequence of expressions. Okay, so let's see some examples of that. So let's go to our Dr. Racket and let's start with some simple lambda examples. So very first simple lambda example. It's just keyword lambda. And we'll start one without any parameters, so empty brackets still need to be there because the parameters will eventually be there. But for now, just empty brackets. And then plus 3, 4. Real simple process. So I invite you to pause this video. Consider what this should do when I run this code. What will the value of this expression be? So pause it, see if you can think it through, and then try it for yourself. All right, so let's run this. If we run this code, we get procedure, and then ... wherever the file here is. Lecture 6.1 SCM is the name of this file. At least it was when I was recording this. So what happened here, we didn't get 7 because it didn't actually run this procedure. When we said lambda, again, remember lambda just sort of means make procedure, so it's just creating the procedure object itself. And this is Dr. Racket's representation of the procedure object. So functions, like the addition function, for example, this is some name bound to some value, where that value happens to be something that can be used as a procedure. So in this case, we made our own procedure. It didn't have a name, so it doesn't have a way of putting a nice simple representation on this side. So it just says, well, this is where you can find it. In this file on line 50, and I believe that one means at the margin. Okay. So there's the first example of a lambda. But let's see, we want to run a lambda. So because this is creating a procedure, if we want to execute it, what we need to do is use it in a combination. Specifically, this should be the first item in a combination. And because this has no parameters, there shouldn't be any other items in that combination. Which is to say, if we want to run this, we just wrap it in another set of brackets. Lambda plus 3, 4, and there we go. One more bracket. There we go. And if we run this, we get 7. So there's the value of the actual thing. So again, this thing, this inner set of brackets here, this says create a procedure, and then this says run that procedure. It's kind of like if we had just said plus, which if we add nothing, we get nothing. All right. Anything else you need to say about that one? No, that's still good. All right, so let's do a more involved example then. So let's do a lambda with a parameter in here. So if I say lambda x plus x3. So again, think, what is the value of this expression? Try and suss it out for yourself. You're probably pausing this video a few times, or maybe you can see it immediately. So figure it out, pause it if you can't, come back. All right, let's try this video. So, so lambda x plus x3, if I run this, pretty good clue it's just gonna not have a value because we don't know the value of x, right? That doesn't exist yet. And that doesn't exist yet because we haven't passed a value into this parameter. And we haven't done that because we've just said lambda. We haven't wrapped it in a combination that will apply lambda to anything. So again, if we want to run this, we would say something like lambda x plus x3, just like before. And then we provide a parameter for that. So it would say 5, let's say. And if we run this, we get 3 plus 5, which is 8. Okay. So again, this whole thing here is the procedure in a combination where the arguments, in this case, are just the value 5. This could have been something else like a plus 1, 2, 3 times 4, 5, 6, let's say. We can run that, and there you go. So again, applicative order says evaluate the sub-expressions. If we evaluate this, we can see we get a procedure object. If we evaluate this, we get some number, presumably 126. Pass that in, and then it adds 3 to it, and we get 129. Sorry, apply that function to it. All right, so that's that one. Let's do one more, slightly more involved one. Lambda x, y, z. So plus times x, y, z, 2, 3, 4. So again, figure out what this thing equals. What's the value of this expression if you were to run it, but figure it out in your head. And now I'll try it out. So again, we're taking in a function and some arguments. The function in this case has 3 parameters, and we have 3 arguments, so that's a good sign. This thing is a procedure, so it just gives us back a procedure object when we evaluate it. 2, 3, and 4 are just integers, so we get 2, 3, and 4 back. And we apply, 2 goes into x, 3 into y, 4 into z. We get 2 times 3 is 6, plus 4 is 10. And we get 10. Huzzah. All right. So there's more practice in the exercise section, but let's go back to, do I have another one here? There it is. Back to our sums here. So, for these ones here, we had some bloated functions here because we had to define identity only so that it could be passed in as term. We had to define inc only so it could be passed in as next. If we want to do this in a sort of shorthand, we could do the sum of all integers from 1 to 100 on a single line now. We could say sum from 1 to 100. Instead of identity, we don't have to define anything. We can just say lambda x. It still has to be a function because it's still going to be used as a function. So we can't get past that part, but our function in this case is just the identity function. And the next one for next would be increment. So we'd say lambda x or y, whatever variable you want to use. And in this case, just add 1 to it. Okay, so a single line, so this is all one expression. If we follow applicative order, it says evaluate this. It's the procedure for summing things. 1 is 1, 100 is 100. This is a procedure for being identity. This is a procedure for being increment. So we have essentially something that looks like this in the first, third, and fourth position in this combination, but only this one is being applied, right? Sum is the one in the front, so that's the one that is the active function, if you want to call it that, and the rest are just arguments to that function. And in this case, we have lambdas, but they're just the procedures. So let's run this. We should get 50-50. The same answer, just in a more compact, perhaps a little less readable format. There is one thing to be said if you have very complex functions. Having the name there is still quite nice. But to that end, there's two ways we could do this. So we've already seen the define for creating names. We could still create names using lambdas if we wanted to put lambdas into our problem as well. The define syntax for procedures that we learned is actually just syntactic sugar. So define, what it does is creates a binding by default. The procedure form, like we see here, where we say define and then something, some sort of combination, and then we have the body for the function. That's a syntactic sugar. It's a nicety for making functions real easy to write, because if you had to use lambdas for everything, it does get a bit cumbersome. But to that end, just to show that these are equivalent, we could say something like, I have one, let's do cube here. So we said define cube x is times triple x. So we could say same thing here, define, I'll use the same one, cube x is 3x's. Or equivalently, so I'll say equivalent, we could say define the variable cube to be the lambda that takes in an x and has the body times x, like that. So these two functions do the exact same thing, these two expressions or these two special forms are saying the same thing. They both say create a procedure object and then bind that procedure object to the name cube. This form is just a little bit simpler to type and read, so it's the preferred form, but they do the same thing. So the lambdas that we're seeing are always there. They're just sort of hidden at times to make our lives easier. All right, so let's do some more examples here. Again, for each one of these, pause the video, see if you can't figure it out before you see the answer. I'll walk through the answer, but it's just better if you try it yourself first. So define some function to be lambda xy. Let's clean this up a little. Let's do that. Times plus xy2. Oh, I left that as define. There you go. Define. F54. Let's call this a simple one since we just learned this syntax. Try it out, see if you get the value. Okay, so a shortcut to this is that there's exactly two variables. They show up in the same order every time. We have exactly two arguments. So you can probably just assume what's going to happen and just boil it down to this expression, which you should be able to solve from, well, honestly, before this course even. But let's walk through it and understand how everything works here. So in this case, we're saying define f to be a lambda, which means the special form says get the value of this expression. The value of a lambda expression is just the procedure object. So it says bind this function to, bind this symbol f to the function or the procedure that comes out of the lambda, which is the function that says x plus y times 2. All right, so that means the name f refers to that procedure. We're going to pass 5 and 4 into f for x and y, and then sure enough, we'll do exactly just that expression. So 5 plus 4 is 9, times 2 should give us 18. Run our code, and we get 18. All right, let's see a more involved one here. Let's start here. What if I were to say lambda ijk plus times 3I minus jk 3, 2, 1. So you might want to pause this one because generally speaking, these things become very hard to read very quickly. More and more practice will give you the benefit of being able to interpret them more naturally, but they are pretty unnatural to begin with. So pause the video, see if you can't work your way through this. And welcome back. So to solve this function, or to solve this, this expression, again, just use the regular eval apply. So to break it down, it's pretty easy with the bracket highlighting. So we have, the outer combination has 3 sub-expressions. One of them's a lambda. We have 3, 2, and 1. So we're going to apply this procedure to those values. Okay, so that lambda has three parameters, I, j, and k, where I gets 3, j gets 2, and k gets 1. So we say 3 times 3, j minus k is 2 minus 1, which is 1. So we get 9 plus 1 should give us 10. Run it. Sure enough, we get 10. All right, try another one here. Let I be 3, j be 2, and k be 1. And in the body of this let, we'll say plus times 3i minus jk. What is the value of this expression? Bearing in mind the value of the previous expression, which bears no resemblance, I'm sure, was 10. All right. So let's walk through this one. So we know how lets work. So a let is a special form that says create these bindings, and then using those bindings, execute or find the value of this expression. So those bindings are, we bind I to the value 3, j to the value 2, k to the value 1. This is sounding familiar. We say 3 times 3, which is 9. We get 2 minus 1, which is 1. And then we say 9 plus 1, which gives us 10. Run this, and sure enough, we get 10 both times. So this highlights an important point. You might recall I mentioned when we were talking about lets that lets are actually procedures in disguise a little bit. They are creating their own scope, and the only way you can get scope is with a procedure. So let is actually syntactic sugar for a lambda. Right? If you had to say lambda every single time and then pass in values, it wouldn't be nearly as useful. A let says, well, up front, I need these variables, and with those variables, I want to compute this expression. But that's pretty much what a lambda is saying as well. It's just it's a bit unnatural. You have to use the word lambda, which doesn't really work the same way as let. Let has intuitive or mathematical meaning, at least, where let I be 3, let j be 2, let k be 1. It grammars. Whereas lambda I, j, k mention the expression, and then 3, 2, 1 doesn't really tell you immediately what's happening. So syntactic sugar is quite nice here. It hides all that information away, that you are in fact creating a procedure and applying that procedure to these values, to the value 3, 2, and 1. Which also might make you appreciate a little bit more why a let's binding section doesn't contain the existing bindings, right? Why they're not sequential, why we can't use the value of I in the definition of j. You wouldn't do that here, right? You wouldn't say plus, or let's say minus I1. You wouldn't say that when we were passing that into a lambda, because I doesn't exist outside that lambda. But if a let is just a lambda, the same rules have to apply. So we can't use the binding or the parameters here outside of the area where they're valid, which is the body of both the lambda and the let. Okay, so lets and lambdas are the same thing. You can translate them one to one. Again, the parameters and the arguments make up the binding section, and then the body is essentially one to one. We have a scope, and all those rules work the same as well. All right. Let's try another example here. So, say lambda arg. Shrink this down a little bit just so we don't go way off the screen. arg2, 3, and then wrap that in a bracket and say lambda xy plus times 2x y. Y indeed. So what is the value of this expression? Again, pause, see if you can't work your way through it. This one's deliberately confusing. Okay, So the key to this one is that we have only lambdas in the expression, right? We have one lambda as the first element in our combination and a second lambda as the argument to it. But if we look at that first lambda, that's convenient that we have a lambda or a procedure as the argument, because the way this first procedure works is it takes the argument, or the parameter rather, and applies that parameter, which is called argument, to the values 2 and 3. So this thing here needs to be a procedure because it's being used as the first element in a combination, so it has to be a procedure to be valid. And it just so happens what we're passing in is a lambda. So we take this function, or rather the function this lambda conjures, which does this addition and multiplication, and essentially substitute it in your mind here. In fact, let's do a substitution model for this. So this whole thing is one big expression. Now again, with substitution models, clarity is more key than accuracy, which sounds terrible, but it speaks to the fact that I don't want to use these procedure definitions because they're kind of obtuse. They don't really tell you anything. The lambda at least tells you what parameters we have and what that function is going to do. So in our substitution model, I'm going to leave these lambdas as lambdas, at least until we apply them. Once we apply them, then we're in the body of that lambda just like we are in a function. So the first line of our expression says take this lambda and apply it to this lambda. So take the procedure objects and pass one into the other, which means in the substitution we take the body of this, the body of the applied procedure, and substitute the value, which would be that bracket, for the parameter. So arg becomes this lambda, and now this is looking like the other lambda expressions that we've seen. We have a combination where the first element is just a lambda, a procedure, and the next two, the arguments, are integers. So 2 goes into x, 3 goes into y, and we get 4 plus 3 should be 7. Run our code, and we get a 7. Okay. Fun. Let's do another one. Find fun x. All right, and inside fun x, we will say lambda of some variable y, and if x is less than y, let's put an if in here, it's been a while, then we'll return x, otherwise we'll return y. That closes the lambda, we'll pass it a 2. Now, before we get any value here, this is just defining a function called fun, where the body happens to involve a lambda somehow. But before anything actually happens, we'd have to say fun of some value to start the process. So let's apply this function to an argument and see what happens. So fun of 3. 3 goes into x, and then we say evaluate the body of this function. So the body of this function starts with a lambda and the value 2. Okay, well, if we apply this lambda to the value 2, 2 goes into y. And then we evaluate the body of that lambda, which says, if x is less than y, return x, otherwise return y. We know what y is, because y is a local parameter right here. It's the value 2, we just saw that. But what is x? Well, thinking back, or even just, I suppose, intuiting, the only other x in this value, in this example is the parameter in the enclosing scope. So remember, lambda has its own scope, sort of a nested scope inside fun here, where the value y exists. But if I said y out here, for example, that wouldn't mean anything. That's outside the lambda, so it doesn't have a binding for that value. But inside this lambda, it has its own scope where y is a local variable. X, however, is not bound locally in that scope, but we do find it in the enclosing scope here, which we saw was the value 3. So if 3 is less than 2, that's false, so we should return 2. Run our code, and we get a 2. Alright, so just like with nested functions, lambdas can use variables from their enclosing scope as well, that is to say free variables, in the exact same way. Same rules apply because, in fact, the functions we were using have always been lambdas. Alright, let's do one other example here. If I use the name foo, I'm running out of names. Func, foo, f, I've used all the good ones. Define my function x. And inside this function, it's going to be pretty similar. I'm going to say lambda y, and then just simply plus xy. Now, if I run my function, all one word, on the value, say 3, what is the value of this expression? Let's pause, see if you can't figure it out. And I'm actually just going to run this and see what happens, and then we'll explain what happens. So if we run this code, we get a procedure object. So I'm just going to type this in here, procedure. Now, why do we get a procedure object? So we called my function with the value 3. 3 goes into x, but then the body of my function is just a lambda. It's not like the previous example where it was a lambda applied to some value, that is to say, evoked and walked through the body. In this case, we just return the lambda itself, or the value of that lambda, which, as we know from our previous examples, is just a procedure object. So if I wanted to actually do this addition, the procedure that comes out of my function 3 here is just this lambda. So all I need to do is provide a value for this parameter y, and then it'll walk through the body using all the actual work. So we'll say my function at 3 like before. So if this is a procedure, it should be the first element in a combination, something like my function 3, 2. So if this first thing here returns that lambda y plus xy, now we're saying lambda y plus xy at 2. Which should say plus 3, 2, which should give us 5. Let's run this, and it does give us 5. But let's take a close look at this just to see what's going on here. If I say my function 3, 2, if I take this line here, but I replace it with this lambda here, copy and paste. When I do the apply step, when I take this 2 and put it into y, the body changes into, or sorry, our expression changes into the body of that function, which is plus xy with y bound to the value 2. But this x here needs to have the value 3 as well. But if we're out in the global scope here, that x, that shouldn't exist anymore, because that's inside the local scope of my function, right? We called this function, what we got back was a lambda, and then we ran it. But if we run our code, we can see that 5 does in fact come out as the result here. So why and how this works is the subject of the next video. And I will see you guys in the next video.